Welcome to the final lecture of this series. After 13 weeks, I'm pretty sure that you are familiar with basic techniques to perform derivative pricing, that you understand the main principles about implied volatilities, about simulating of the processes, and how it is to simulate and how is it to price a derivative. Now it's time to summarize what we have learned. So today we will just go through all the lectures that we have covered, and I will highlight the most important subjects that we have discussed in this series. As you can see in this series, we have covered a rather broad spectrum of the topics in computational finance. We started with the introduction, some general settings about the stochastic differential equations, stochastic processes, and options. We also discussed the concepts of implied volatilities, how to include jumps in the stochastic differential equations, what is the affine class of affine diffusion processes, and how this class can be used for calculation of option prices. Then we even went further. We discussed extension to stochastic volatility models, where volatility is not only constant or time dependent, but it's also stochastic. And then we applied numerical techniques, so very much computational aspect when we spoke about Fourier transformations for option pricing. So this technique, which is extremely efficient, we dedicated quite some time to that. Of course, pricing with fast Fourier transformation and very fast pricing is used mainly for calibration of derivatives. Once we calibrated the model, then we can perform simulation with using Monte Carlo or PDEs. And then we have lecture number 9 and number 10 when we discussed different aspects of Monte Carlo simulation, which applies not only to one or two dimensional processes, but applies to highly dimensional stochastic differential equations, which can be used to price some exotic derivatives. Then we also went through the hedging and how this hedging can be done under Monte Carlo. And then we also discussed the concept of the Greeks. The last two lectures, so forward start options and exotic derivatives, those are, let's say, the summary of this series, where we have used all the knowledge that we have learned about the pricing, and we extended that with some particular products that are forward start options, so options that are not only plain vanilla options, but there are also some more exotic derivatives. We have also spoke about the stochastic volatility with jumps, so the extension of the Heston model, and how to structure a product such that our client who buys a derivative can get price which is reduced. So this was covered in lecture number 13. Let's now go through the particular lectures, so one by one, and I will highlight the most important elements of each of the material, each of the lectures we had covered. So in lecture 1, this was obviously an introduction to the course. So we have spent some time on discussing financial engineering, different markets, and different asset classes. In each asset class, you can apply different models. So different asset classes, they have different principles. They have, of course, from the pricing perspective, the pricing principle and the risk neutrality is always the same. However, each individual market may have different products that are available for pricing, and different instruments can be used, for example, for calibration, or they are simply just different markets, like, for example, cross-currency, equity, interest rate, and so on. Then we had also, we spoke a little bit about the stocks and dividends. So how to, what are stocks, what are dividends, what are the main principles behind it, and why they are stochastic, for example. We also covered the relation to interest rates and what is the relation between stocks and interest rates, how the volatility plays a role. Of course, those are very important components, especially once we talk about options and payoffs, which is also discussed in the first introductory lecture. So this was just the introduction to the series, and I think that gave you strong fundamentals to go on to understand where, in which asset class, the pricing models can be applied. In lecture 2, we concentrated further. We discussed different types of options, so how the trading of options is performed, and also we said a few words about hedging. We discussed also commodities, first currencies and cryptos. In particular, here I have brought Bitcoin and also its extreme volatility that we can observe in the market. And then, given that information, we discuss how to perform pricing of call and put options and how this is related to hedging. I think at this point, the most important element to know and to memorize is that hedging is the price of a hedge. So if you have a derivative, you price a derivative and you set up a hedge, the price of a hedging strategy should be always equivalent with the price of a derivative you want to charge, of the price of derivative that is available in the market. Otherwise, there is some arbitrage opportunity. Of course, in practice, once we talk about selling and buying derivatives, or if we sell derivative to a client, there is always additional premium. This is how we essentially make money once we sell a derivative. The next step, of course, once we talked about calls and put options and how this is linked to hedging, then it's time to go into mathematics and discuss modeling of different asset classes, or actually asset prices, and randomness. How this randomness can be measured, why stocks are volatile, and what mathematical tools can we use to describe random behavior of a stock. Of course, randomness in stock processes is related to stochastic processes and which describe the random behavior of a stock. But having stochastic process on its own, it's not enough. We always have to have tools that allow us to describe the dynamics, especially if we talk about solution of stochastic differential equations, stochastic processes. And that is handled by Ito's lemma. So Ito's lemma is a very powerful machine that is used to derive the dynamics and also allows you to compute the solution for stochastic differential equations. As we have seen already in this course, stochastic differential equations are one of the most important ingredients once we talk about pricing. Everything is related to volatility, uncertainty, and randomness. So Ito's lemma is a crucial element for that. Lecture 3, then we went a little bit further into details about the simulation. So you remember we spent a lot of time about simulating in Python. So Python is our tool for simulation. And then we discussed first how to simulate in Python paths, so how to simulate a random stochastic differential equations and how those can be used for pricing. Essentially, in computational finance, or actually in finance in general, we try to describe the real behavior of a stock, so its movements, stochastic movements, by a model. And for that, we use stochastic differential equations that can be or has to be programmed in order to perform pricing. Of course, in some cases, like for example in Black-Scholes case, so which is also discussed in lecture number 3, Black-Scholes case, because of the simplicity of the underlying stochastic differential equation, we don't need to simulate. If we talk about the pricing of a derivative, we can simply just evaluate Black-Scholes formula. But we know that Black-Scholes formula for pricing, it is not good enough. Black-Scholes model, it is not rich enough to describe well implied volatility smiles or skews or hockey sticks, etc. So at this point, I would stress that please concentrate what are the advantages, disadvantages of the Black-Scholes model, how you can, in which scenario can you use Black-Scholes model, in which scenario you cannot use Black-Scholes model. This is the main takeaway. This question would be, if I have a pricing of European call option, is it enough if I use Black-Scholes model, or I should go for something more advanced? So this is the crucial question that many people fail. If you have a pricing of a call option or put option with particular strike, it's often not necessary to use any more complicated than a Black-Scholes model. But of course, the question is, what is this pricing only standalone, or you just price a European option, or this is element of a much more complicated framework where you would like to, when pricing of an option is just an element, once you talk about hedging of some maybe exotic derivative. So we always need to have a bigger picture in order to make sure that you have to have a consistency between all the portfolio derivatives that you have to price. Hedging of the Black-Scholes model, this is also very important. Later on in, I think, in lecture number 12 or 13, we also simulated hedging strategy when we have calculated P&L, and then dynamically we have analyzed the P&L behavior depending on frequency and of our hedges, and also volatility of our stochastic process. So the hedging argument for Black-Scholes model, it is very important. Another important building block or important tool that is used often in or always in derivative pricing is the concept of martingales. And martingales, how they can be used in option pricing. So this is something that it is crucial, and that's a very important element of this course. I have also spent some time to show you how coding of martingales in Python can be performed and how to check whether the process that you simulate is a martingale. I have also repeated many times what quantities, what tradable asset class tradables are martingales, and how to check them that they are indeed martingales, and how this is related to measure changes. Another important point in this lecture, it is a relation of a risk neutral valuation and Feynman-Katz formula. So this is a relation between pricing using PDEs and Monte Carlo simulation, and conditional, or let's say expected value and discounted future expected value. So this is super important for computational finance. This theorem or this step actually allows us to not only solve PDE using partial differential equations, some PDE techniques, but allows us to simulate stochastic differential equation and perform expectation, calculate expected value of the future payoff, and then discount today. So this relation is super important for everyone who's dealing in computational finance. Measures and impact on drift. This is also important element. So how, if I give you a stochastic differential equation, how to judge whether the process that is given, it is under a risk neutral measure, is it P measure, or is maybe there is some other measure. So how to, if you look at the process, how to say whether it is a martingale, and how martingality and also how measures affect the drift. So this was the also element of this lecture number 3. And finally, here we discussed the closed form solution for the Black-Scholes model. So I would say lecture 3 gave us a very insightful, very, let's say, deep dive into materials about pricing of simple European options, about martingales. We have also learned about ethos lemma, martingales, drifts. So I would say those are really important elements. Those are really crucial elements if we talk about the pricing of derivatives. In lecture number 4, we concentrated on the idea of implied volatility. And this was a rather practical lecture where we discussed the deficiencies, the limitations of the Black-Scholes model, and how we can actually calculate what is the market practice once we talk about the Black-Scholes model, and what is the quotations used for, what is the standard that is used for to quote European type of options. Of course, this is related to Black-Scholes model, so I think this is the key element here. Again, as I already have repeated many times, once we talk about implied volatilities, it is always about Black-Scholes implied volatilities. We never talk about Heston implied volatilities. Sometimes people use the concept of normal implied volatilities, but then you have explicitly mentioned that. Normal implied volatility would be implied volatility, which is computed using arithmetic Brownian motion instead of geometric Brownian motion, as we have it done for the Black-Scholes case. Calculation of implied volatilities relies on solving some numerical problem, and that can be done with the Newton-Raphson algorithm. So here it's important to understand how Newton-Raphson works, what is the convergence of it, and what are the disadvantages, what are the limitations of the approach. Of course, here you can also think how the Newton-Raphson approach could be simplified or can be replaced with alternative technique. Then the concept of a time-dependent volatility. So of course, once we have Black-Scholes with constant volatility, we know this is not ideal for pricing. So the question here, if we have time-dependent volatility, can this actually facilitate us with implied volatility smile or skew? And of course, that's not the case. By having implied volatility sigma, which is time-dependent, we can only make sure that our at the money term structure of volatilities is well fitted. However, outside at the money, there is not enough degrees of freedom to fit outside the at the money options. So this is let's say a tricky question, but that also indicates that the Black-Scholes model, the extension by making some parameters time-dependent, this is not enough to have a good fit to the implied volatility surface, for example, which was also discussed in this lecture. And here we have a summary of the limitations of the Black-Scholes model. So I would expect that each of you understands what are the, of course, parameters, what are the assumptions, and how to deal with them. Which of the assumptions are crucial, which of the assumptions are not so important. In lecture number 5, we discussed the concept of jumps and how jumps can be incorporated in the Black-Scholes model. Of course, we started first by inclusion of jumps into the stochastic differential equations, just to mimic the behavior of stocks in reality. So we know in reality, stocks are not always smooth, or let's say diffusive. Smooth maybe is not the best word here because it's a Brownian motion, but they are not continuous, or they are continuous. But in practice, in reality, we see that stocks have behavior. It's often jumping, and that can be done by inclusion of a jump process into the stochastic differential equation for diffusion for the stock itself. In this approach, the jump process in this lecture was modeled by Poisson process. I have also discussed how to perform the implementation in Python and how to extend ethos lemma such that jumps can be also handled in that. So it's also very, very important element. Once we have jumps and we change measures, because pricing of options is always under the risk neutral measure. Once we talk about measures, it is also important to make sure that by inclusion of jumps, we haven't spoiled, or we haven't ruined the risk neutrality that we would have for a simple Black-Scholes case. So this is also related to the martingality and ethos lemma also in a jump case. Once we perform pricing, then it's not only PD, but we have a PID if we have a jump included in the process. So this is also the key takeaway from this part. By inclusion of jumps, we can improve not only the ADM calibration, but we can also generate skew in the model, and that's discussed in this part. So here we calculated number of implied volatilities for different models, where we were changing parameters of a jump process. So here we also can analyze what is the impact of different jump parameters on implied volatility shapes. And here we could actually see that by changing jump parameters, we could generate skew, we could have some control, but this control was not maybe flexible enough so that we could calibrate to the market data. Another limitation of the jump processes is that the hedging is typically more expensive than if you would have a smooth, diffusive type of process as the underlying. And for that reason, we later discussed the concept of stochastic volatility models. Since the Black-Scholes model is not enough for calibrating to implied volatility surface, also by inclusion of jumps, we are not able to handle sufficiently good the calibration. We need more extensive modeling. So this means we need more flexibility, we need more stochastic differential equations that would describe the dynamics of the process, of the stock process. Of course, once we increase the dimensionality, we include more stochastic differential equations, then the complexity of the model increases. For that reason, we need to have fast tools that will able us to calibrate or to perform pricing of European type options in a very fast way. To achieve that, that will be discussed, of course, next lecture, the models under the consideration need to belong to the affine Jump-diffusion class. And this is the main objective of lecture number 6. Of course, we started here with some motivation about how to choose pricing models, how this is related to calibration, pricing of exotics, etc. Here we also discussed the motivation for Fourier. So this is again a motivation why we should use fast techniques for pricing of European options. And overall, in this lecture, we concentrated on the conditions that models or stochastic differential equations need to satisfy, such that the model is allowed to be, or model is able to be used within the affine models within the Fourier transformation. And so in this framework, basically in this lecture, you can consider we define the main conditions that stochastic differential equations need to satisfy, such that we can use those models in a fast calibration to European type of options. Of course, here we also discuss high dimensionality, what are the conditions in the very high dimensions, and how this class also is able to handle jumps. Of course, our scope is limited to the jump cases where there are no correlation between jumps and diffusion, but in general, this correlation could also exist. However, this is rather impractical and does not happen too often. So main takeaway from lecture number 6 is what are the conditions regarding stochastic differential equations such that the model of under consideration belongs to the affine class of diffusion processes. And the most important is, why do you need such a class? How this is important for pricing, and what is the bigger picture of a fast calculation. Of course, we are not performing fast calibration because we just want to have things fast. This is typically associated with a problem of calibration. In the problem of calibration, if we have multiple stochastic differential equations with many parameters, then you can imagine that pricing of an option, it's not done 1, 2 times, but it can be done hundreds of thousands of times. And each calibration or each evaluation of an option will take a few seconds. And then if you multiply, of course, number of times few seconds, this could be a very substantial amount of time. For that reason, we need to have a method which is extremely fast, which allows for very fast calibration. Lecture 7 is the lecture where we covered one of the most important processes or models for pricing of equities and stocks. This lecture was about modeling using stochastic volatility. This kind of models, including stochastic volatility, give us enough flexibility once we talk about calibration to European surface. So surface of implied volatilities from European type options. So the model which allows for calibration to the whole surface, it is flexible enough. And of course, this flexibility comes by usage of stochastic volatility processes. In this lecture, we discussed in particular the Heston model, where we also spoke about the correlation of of differential equations. So how to correlate processes once we deal with more than one dimension. Of course, until now, we didn't need correlations because we didn't deal with multi-dimensions, except for jumps where we had zero correlation, so we assume independence. But in a Heston case, we need, let's say, we need correlation between stochastic differential equations. Also, in this lecture, I have shown you that correlation impacts of the relation between stock process and also the variance process. Correlation has a very important role. It gives us extra flexibility once we talk about generating different implied volatility surfaces. Of course, as for pricing for any model, we discuss pricing PDE and how to arrive at the pricing PDE. This is also a very generic approach. This would be applicable to any stochastic differential equations. Impact of the stochastic volatility model on implied volatilities. So this is also important to understand that, in particular for the Heston model, one of the greatest advantages of the model is that implied volatility shapes are easily controlled by the model parameters. So by changing a parameter, or approximately which part of the implied volatility surface this parameter will affect. Here we considered only the constant parameters, but in practice, this model could also have time-dependent parameters, would give you even further flexibility once we talk about the calibration. Then there was a small discussion about the Black-Scholes and Heston model. So this is important to know what are the takeaways, what are the biggest advantages of using Heston model, and also what are the limitations. Of course, the limitations in this case comes from the fact that the Black-Scholes model is given analytically. But please think about also in global picture, when would you use Heston model, when would you use Black-Scholes model, what are the differences, what are the common things, and how to go about. So if I give you a model, how would you handle it? And this is related also to materials from lecture 5 and 6, once we talk about affine diffusion models, Fourier transformations, etc. And of course, the final stage, in order to use Fourier transformations, once we know that we have a Heston model under the affine Jump-diffusion framework, we are able to find the characteristic function, and then we are able to perform pricing using Fourier transformations. Once we have a model which belongs to the affine class of processes, we are able to use the Fourier transformation or cost method in particular to perform pricing. And as we have discussed in lecture number 8, pricing of European type options, so we mainly concentrate on calls and puts, it can be extremely fast once we have available characteristic function, and especially if the characteristic function is given in closed form. As you may remember, in derivation of the characteristic function, we always have to solve a system of complex values, ordinary differential equations, ODEs. And this is not always the case that those ODEs can be solved analytically. If, for example, you would have parameters that they are not, let's say, piecewise constant, or they are not constant, but they are time dependent, then those ODEs would not be, you would not be able to solve them analytically. Then essentially you would need to apply numerical technique to integrate those to obtain solutions for those equations, and then those results you can use in the evaluation of the characteristic function. And only then you can apply the cost method of Fourier transformation. So as you can imagine, that could be very expensive, especially since that for every Fourier argument you will need to use some kind of numerical integration in direction of time. So that could be very, very expensive. So you see that this is important, that although your model maybe is more realistic once you consider parameters to be time dependent, you always have to look at the final output. Is your model able to calibrate very well? Can you perform extremely fast evaluations of plain vanilla options? If you cannot, typically such a model will be rejected from the industry because it's not practical, because you are not able to perform calibration in a very efficient manner. So in computational finance, or in financial engineering in general, it is very important that you have a balance between a model which is good enough, or it is performs very well. However, on the other side, you have to also look at the computational cost that is associated. Typically, there is a balance, so you can find a model which is extremely good, it has many parameters, but there is a cost that it evaluates extremely slow. So the calibration part could be extremely slow. And that obviously, this means that this model will never be used in practice. So of course, you don't need to give everything away, right? So you don't need to always concentrate on Black-Scholes, for which most of the derivative pricing you can do analytically. There is some golden middle point where you can actually you can find a model, or you can choose a model which is good enough for pricing, is actually even good for pricing, and at the same time, calibration can be performed very efficiently. Lecture 8, indeed, we concentrated on Fourier transformations. So once we have derived the characteristic function, and preferably this characteristic function is given in closed form, then we are able to apply the cost method or Fourier transform in general to perform something, to perform pricing. Yeah? So in this lecture, we started with just a recovery of the density. So that's the basics that we need to have. Once we have a density which is recovered, we are able to perform integration in let's say integration in the real axis to get the price. Of course, the biggest advantage of the cost method is that we can perform pricing using the cost method of multiple options with multiple strikes. So this means that you don't need to iterate over all the strikes. You can just perform one evaluation, and then you get prices for all the strikes. Of course, to get that working, and get that working efficiently, you have to work a little bit carefully with the matrices and matrix operations. In particular, here the cost method was relying on the composition of the characteristic function. As you may remember, we had this phi Levy, and then we had this element of I u x, and then we have a characteristic function. So think of this kind of decomposition, and that's very beneficial once we talk about the cost method and Fourier transformations. So of course, first we started the density recovery, and then we performed the pricing. And I have also shown you how to do the implementation in Python, which obviously it is a tool which is not only used in academia for your experiments, but more and more it is used also in the industry. So I think knowledge about how to program efficiently, this is great investment for your future career. Efficient calibration, although it's crucial when we accept a model to be used in practice, we also have to concentrate on pricing with, for example, Monte Carlo. So we can, once we have a derivative that we would like to price, and derivative for which we cannot derive analytically the closed form solution, or we cannot use Fourier transformation to get the pricing, we have to either use PDEs or often Monte Carlo, which is often more flexible for pricing of exotic derivatives. However, if you have an exotic derivative and you have, let's say, a contract which involves multiple dimensions, so you have a model with multiple dimensions and contract which is very complicated, essentially what can also happen is that time necessary for accurate pricing is also very high. So this means you have a lot of computational costs involved in evaluation of a Monte Carlo pricing. For that reason, you also need to concentrate on how to improve your Monte Carlo, how to understand where is the error, how to reduce the error, and focus on the most important elements once you perform Monte Carlo simulation. So in this chapter, so in lecture number 9, we focus on different aspects of Monte Carlo sampling. So we started with the integration, so a very simple and very naive way of integrating, however extremely powerful in high dimensions, where we cannot perform sampling, or we cannot integrate in analytically, or even numerically. It could be very, very expensive. I have also proposed show you a number of examples how to perform stochastic integration in Python. So as you may remember, we have integrated Brownian motions, and there were different aspects of integration. And I show you how to look at the error depending on either number of paths or number of the discretization steps. In Monte Carlo, typically those are the main two elements. So number of Monte Carlo simulated trajectories and number of steps that you will have in the intermediate steps in the simulation. Obviously, if you are able to find so-called exact simulation, so your model allows for big time steps. So this is only when you know the transition density or transition distribution, so conditional distribution, then you are able to perform large time steps without loss of accuracy. And this will be discussed in lecture number 10. However, in general case, when you don't know you are not able to derive the conditional distribution, conditional random variable, you have to perform either Euler or Milstein simulation, Monte Carlo simulation. And of course, since you are you have two parameters to change. You have a delta t, so discretization, and also number of paths. It is important to understand which method, in particular either Euler or Milstein, it is more useful and more efficient once we talk about calibrating. So sometimes by reducing the grid size by half, you need to know what is the impact on the error you may expect. There is, of course, no point of just generating thousands of simulations and try and error. You can actually, as it has been presented in the lecture, by essentially understanding how those methods works, you can a priori determine how big the delta t or discretization on your grid has to be, such that you can reduce the error to the satisfactory level. And this is the biggest takeaway from the lecture. Of course, the very important element is that you have a Milstein scheme. For Milstein scheme, you have to perform additional derivations with respect to certain derivatives. And this is important in which conditions you are able to do that, and whenever you are not able to do that. Otherwise, if Milstein would be, for example, always superior to Euler, why would anyone use Euler? So always think about the differences of these two approaches. This is important to understand. What are the advantages? What are the costs? And of course, what are the benefits and what are the costs? We also discussed here the impact of smoothness of the payoff, or in general, smoothness of the function that we would like to approximate using Monte Carlo, and how the smoothness impacts the convergence. What is the impact of a function, whether there is a function which is smooth or it's a digital type of, and how we can see the convergence. Can we actually improve the convergence by increasing the number of paths and time steps or not? So this is kind of also important takeaway, because in practice, once you price payoffs, you price some derivatives, you always also need to think about, is your payoff continuous, is it smooth, or your payoff function also has some digitality. Given that, you may also be inspired whether you should increase number of paths or you should change number of the discretization steps in your simulation. There are also different types of convergence. So this is also, I stressed a lot about the weak and strong convergence. So this is important to understand the difference and in which scenario you need to have which type of convergence is necessary to guarantee the accurate pricing. So this is also a very important part. And then we spoke a bit about standard error, how to measure the error. And this error was put in context of two approaches, Euler discretization and Milstein discretization. These are the two most popular approaches to to perform Monte Carlo simulation in a single or even high dimensions. The Heston model is not only popular because its flexibility in terms of calibration to implied volatility surface and availability of the characteristic function. Heston model also allows for very efficient, almost exact simulation of the Monte Carlo. So once we have a Heston model, there also exists a technique in which allows us to perform very large time steps in the simulation. In this lecture, in lecture number 10, we concentrated on such a simulation, on almost exact simulation of the Heston model. As you remember, for Black-Scholes, we are allowed to, so once we had the distribution, so in a Black-Scholes model, we knew explicitly Ti, it will be Ti plus 1 given STi. We knew the distribution of STi, and then we had an exponent, etc. So of course, this kind of formulation allows us to perform extremely large time steps once we talk about conditional sampling. So this representation allows us to perform any size time steps between two consecutive times. So we can choose time Ti and also Ti plus 1, and they can be anywhere on the grid. And as long we use the exact representation, we can perform sampling without any loss of the generality. In lecture 10, we also discussed this kind of aspects. However, we are not able to perform this kind of exact simulation of the Heston model. We did it in the terms of almost exact simulation. And that was related that although for a Heston model, we can perform simulation, almost the exact simulation of the CIR process, so we can get the conditional sampling for the variance process, so VTI plus 1 given VTI, and this is given in terms of some constant times non-central chi-square distribution with d degrees of freedom and non-centrality parameter lambda. So this was the way how we can perform exact sampling of this distribution. However, once we talk about the stock, which relies on this variance, then we were not able to find this kind of representation. Therefore, for a Heston model, we have almost exact simulation. This means we can perform large time steps. However, those time steps, they cannot be too big. Otherwise, the error will increase. And this is also what we have discussed in this lecture. We analyze how big the delta t, big time steps, how they impact the error of our simulation. In this lecture, we also concentrated on the CIR process and what are the problems with the CIR. So of course, the main limitation or biggest issue of the non-central chi-square is that it is limited, it has only positive axis, right? So we don't have any realizations for the CIR process which are below zero. And once we perform Euler or Milstein discretization, then we have a chance that some of the paths will become negative. And that's a problematic, especially since that in a CIR process, we have a square root of variance, which essentially destroys the simulation. And in this lecture, we also discuss what are the possible ways how to perform the CIR simulation in an efficient way. Another takeaway, of course, we also discuss on the Python implementation different ways of convergence. So we also analyze the error that you can see by different choices with respect to the variance process. The biggest takeaway here is maybe about the CIR process, is about the Feller condition. So under which condition the paths are guaranteed to be non-negative, and when we are actually can perform Euler discretization without any risk that paths would become negative. So this is something to keep in mind. The Feller condition is a very important condition for the CIR process, and depending on the different configuration of the parameters, you may have different issues with the model. However, in this setting, once we talk about almost exact simulation, the process or this representation for the conditional sampling, it is not really concerned, because since we know the exact distribution, or we know conditional sampling exactly what is the distribution, then we are not really concerned about whether paths are negative or not, or can be negative if you perform some Euler. However, there is some cost to pay because not always, in not every library, sampling from non-central high-square distribution is efficiently implemented. So for that reason, in industry, there are also other methods how to perform sampling from non-central high-square in a more efficient way. However, these days, I think most of the computers and most of the uh, latest libraries that allow for efficient sampling from the non-central high-square distribution. Therefore, we can perform large simulation steps without loss of the accuracy. However, once we talk about the Heston model itself, not only the variance, then there could be some additional error related to the two-dimensional sampling from the stock process. Until now, we talked about the calibration. We also spoke about the pricing of an exotic derivative. But what happens if you have already traded this derivative and you have basically sold it or you bought it? Essentially, from that moment on, this contract is in part of your portfolio. It's a part of your book. Um, and what that means, it means that you have to maintain the contract. This means you have to take care of it. What that also means is that you have to hedge the associated risks. So if you're from banking perspective or any financial institution perspective, it is important that contracts which are in a portfolio, they are not exploding, let's say. Right? So if the market moves, then the risks or the losses, potential losses, are not increasing. This is associated with the concept of hedging. Hedging essentially means reducing the exposure, reducing of risk, typically by having the underlying or selling the underlying, especially if we talk about the delta hedge. In lecture 11, we concentrated on that aspect of a derivative. So essentially, process of hedging always starts after the trade has been done. So once we sold the contract, bought the contract, then we start with a hedging process, and which is also very, very important because hedging, if you sell or buy derivative, you do it only once. However, hedging, it will take until the maturity of the contract. So even I would say hedging sometimes is more important than just the pricing of derivative, because every day, whenever you evaluate your model has to perform very well for the purpose of hedging. And of course, once we are able to calibrate the model, so this is what we already discussed, hedging part is super important. In practice, you would hedge all the risk parameters. So if you recalibrate your model and your model parameters change every day, that would imply that every day you will need to re-hedge the risks associated with each of the model parameters. In lecture 11, we looked at one of the most fundamental type of hedging with delta, so delta hedging. In these experiments here, we talked about, we have looked at the hedging with buying or selling of underlying asset that your option was defined in terms. So this was in particular, we looked at the pricing of option call and put option, and then we were hedging using buying or selling of the underlying. We also used the money savings account as the, let's say, a place where we could put our money, and then also money was could be borrowed from that account. In this experiment, actually, we confirmed that at the end, if we perform, of course, given the assumptions of the hedging, so given the assumptions of the model about transactions, etc., in this experiment, we have shown that if we have an infinite number of hedging moments, so in particular Black-Scholes model, if we increase the frequency of hedging, then the P&L or the effect of market fluctuations, market movements on our portfolio is reduced. So this means P&L, it is zero. Of course, also keep in mind that zero is not really successful trader. You're not successful trader if you have a zero on your P&L. Obviously, the extra profit or the profit that you would make, it is at the inception. So essentially, once you sell a contract, then you charge additional premium that is going to be left over after the contract matures. So this is the main assumptions, a main concept of the concept of hedging. Here we also talk about the effect of jumps. So everything relies, of course, how you choose a model. If the model that you are using for simulating it is realistic, first we have simulated the model. Let's say the market we assume to be a Black-Scholes. and we perform hedging according to Black-Scholes. So we had a perfect consistency between the market and also model used for hedging. But however, we also discuss the aspect that when we have a market is input jumps. However, we perform hedging without model with jumps, and we could easily see that there is a problem, and we could see that we could not that we always generated some losses in our strategy with delta hedging, and that's the biggest problem with using jumps, or if the market that you are selling your derivatives, if there are huge jumps, that's very difficult to perform hedging in a way that you are not losing money. And this is another takeaway from this lecture. Then we also discussed different aspects, different possibilities of hedging. So it's not only delta hedge, but also gamma or vega hedging. And that depends on the also type of model we are having, especially in a vega hedging. For Black-Scholes case, we don't need to really care on vega. That was also illustrated in a Black-Scholes experiment. This is related to the fact that in a pure Black-Scholes model, we have constant volatility. So essentially, once we have constant volatility, there is no uncertainty associated with that parameter. So there is no need to hedge that. Of course, in practice, once we recalibrate our model on a daily basis or weekly basis, then of course, volatility that we will calibrate would be different. And that would imply that we need to also perform hedging of that parameter. Hedging is associated with sensitivities, so it's sensitivities of your value of your derivative to particular model parameter, or is it initial stock or the stock that you have, or parameter like interest rates or volatility. And for that reason, it is also important that your sensitivities are fast and they are accurate. And so for that reason, we discussed different three methods of how to improve the computation of the Greeks. We had a finite difference, pathwise sensitivities, and likelihood ratio method. I think that was what we have seen from the experiments. Pathwise sensitivity was one of the most accurate ones. However, finite difference was the most flexible. It was always applicable. However, in terms of efficiency, pathwise sensitivities were much better. Of course, we are not always able to perform pathwise sensitivities, and you have to learn from this lecture why it is the case. What are the assumptions of pathwise sensitivities? In lecture number 12, we concentrated on pricing of a little bit more advanced and more complicated derivatives as we have seen before. So lecture number 12 was concentrated on pricing of forward start options and looking at the variance swaps, so contracts which rely on volatilities. The essence of the forward start options was that that the option will start in the future. So it is not an option which we buy and the exception is today, but option in which the initial stock will be known only in the future. And that required in the evaluation, that required that we need to calculate additional expectations. So we had this uncertainty of the initial stock value. And that also brought us additional complexity once we talk about the characteristic function. In characteristic function, we essentially needed to solve two expectations. One for characteristic function, and second for the conditioning. So we had two expectations. One was the characteristic function, and also outside we need to solve additional characteristic function. And that happens that for the Heston model, we were able to derive that analytically. Of course, once we increase the complexity of underlying, of the option, so instead of European type option, we concentrated on a forward start option that increased the complexity of the characteristic function. It's a completely different assumptions because we need to have an additional condition on the future time. It's not only about t0, but the start point is in the future. However, we are looking for the value from perspective of today, which seems to be a little bit maybe a difficult concept. For Black-Scholes model, we were able to find the characteristic function and also the evaluation of the forward start options analytically. And once we also derived the characteristic function for the Heston model, we were able to price options with that. We also had to talk about forward implied volatilities. So once we talk about implied volatilities, we always have in mind Black-Scholes. If we derive prices or we calculate the prices for forward start options, and we talk about implied volatilities, we have in mind forward Black-Scholes implied volatilities. So it's always about Black-Scholes, whether it is just a regular European type of implied volatility or it is associated with a forward start. And that's a big difference between these two approaches. And here we discussed how to perform implementation in Python. And as an extension for the Black-Scholes and a Heston model, we have also discussed the model of bytes. So it is a model which includes additional jumps in the dynamics of the Heston model. In essence, and this is also a practice, jumps are considered to be independent element of the model. So that means that if we have characteristic function, independence essentially means that we can just multiply characteristic functions. So adding jumps that they are independent to any model you can think of, typically it is considered to be rather easy exercise. However, the complexity associated with either hedging, that is difficult for jumps, or calibration of the parameters, that's very high. This means that it's not, it is maybe easy to include such a model in your dynamics. However, it is difficult to maintain, and maybe the benefits that you have are not very great. So Bates model, it is popular model. However, Heston model is always the core. So it is not really, Bates model is not really a super important alternative. Mainly if people talk about Heston model, you can always switch and use the additional jumps. However, the Heston model and the theory behind the Heston model stays almost the same between the two models. Here we have additional jumps. And finally, in this lecture, we talked about variance swaps and about the product of volatilities. So here was important the relation between strange representation of the variance swap contract and the relation to the conditional expectations or the expectation we have derived using the Black-Scholes dynamics. The most important, very interesting element of that was that at the end in the variance swap, we had very interesting expectation, which was expectation of a log st, right? So this was t0. And that was in particular very interesting because once we talk about martingalities, this quantity is not a martingale because we cannot really buy or sell logarithm of stock. So that was interesting. And please think about it. How would you solve such an expectation? And how would you actually calibrate such a model to which implied volatility, which strike would you use to get this expectation under the assumption of the Black-Scholes model? In this lecture, we considered multiple different features that we can consider to be used in a structuring of a product. We talked about the binary and digital options, path-dependent options, barrier options, and agent options. So we could either reduce change the payoff such that the upside potential is limited, and that was in particular case once we talk about the binary options, barrier options. However, we could also change not the payoff itself, that we limit the potential, but we could reduce the uncertainty. And by reducing of uncertainty, we spoke about averaging of the underlying. So instead of looking only at a particular asset at given time, some clients prefer to reduce the uncertainty, and that can be just computed using average. So average has a smaller standard deviation, less uncertainty than just a simple underlying, and that obviously would translate to the lower price of a derivative. Those three categories, or these three different types, those are popular, and of course they may vary from the different asset classes. The popularity may vary, depends on whether it is FX, interest rates, or equity. Some of these contracts are more or less popular. We also discussed multidimensionality. So what are the techniques that we have to apply once you talk about the pricing of a contract which involves multiple assets, like for example, basket options, which can contain hundreds or thousands even different stocks. And what are the numerical techniques that you have to know to evaluate such a basket? I think this lecture number 13, was essentially a summary of what we have learned. So we collected all the knowledge about the calibration, about Monte Carlo sampling, and we just concentrated on particular tuning of the payoff and what are the options, and we concentrated on the options that we have in order to structure the payoff for our client. In the industry and also in the literature, the range of possible contracts that we may think, it's much broader. There are many more possibilities, and those will be discussed in the follow-up courses. However, I think at this point, those elements or those ingredients that you have learned here, those are building blocks for much more advanced derivatives. I think this is the final lecture of this course, and I would like to congratulate you if you have followed all these 13 or actually 14 lectures. I think it's a great achievement, and I think you are prepared to be a working industry or continuing with other courses that they can help you with gaining more and more knowledge about computational finance, financial engineering, and derivative pricing. Congratulate you, and I wish you a successful career in finance.